Hey everybody, this is for J, impact of mass on conservation of energy. It says the scenario is an apparatus to determine coefficients of friction is shown below. The box is slowly rotated counterclockwise. When the box makes an angle theta with the horizontal, the block of mass m just starts to slide. At this instance, the box is stopped from rotating. Thus, at angle theta, the block slides a distance d, hits the spring, a spring constant k, and compresses the spring a distance x, which isn't labeled on here, before coming to a rest. All right, so first thing up is they want us to do an energy bar chart here. So it says draw a qualitative, meaning we don't have to worry about numbers, energy bar charts that represent the energy of the block, earth, spring, box system. So block and earth means we can include gravitational potential energy, and spring means we want to include elastic potential energy as well. Okay, so it says that it starts from rest, so there's no kinetic energy. And it's above whatever we want to call the ground. So it's got gravitational potential energy. How much? I'll just draw 4 bars because that works out nice and easy there. It hasn't compressed the spring at all, so there's no elastic potential energy. Now, sometime later, we're sliding down, and it says x equals d. So we're just about to start compressing that spring. You can consider we haven't hit the spring yet. So the gravitational potential energy will drop. How much? We don't know, but let's just pretend here for a second that it drops to half. It's lost half of its gravitational potential energy, so 2 bars instead of 4. Now, the tendency right away is to say, the kinetic energy is the other 2 bars. And normally you would be right, except this time they said there's friction. So let's say the kinetic energy only goes up 1 bar there. And so then, where's that other missing bar to get us to a total of 4? It's in thermal energy. Friction will change mechanical energy over here into thermal energy. So we still have 1, 2, 3, 4 bars, just like we did over here. That's the key concept. All right, now we come over here. This is x equals xs, meaning we've compressed the spring to its full value there. By the way, when we compress the spring, we will have come to a stop, so no kinetic energy again. What we call the ground is sort of relative, but a good place to call the ground is where it stops in the end. So let's say no gravitational potential energy. So now let's look at the spring. We'll have compressed the spring some here. Let's do the spring in green here. So the potential energy of the spring is 2 blocks, let's say, there as we've compressed it. And then the thermal energy will still be going on. It's still touching that surface, so it's still heating up. So our thermal energy should have gone up as well. Notice I've got 1, 2, 3, 4 blocks here as well, just like I did in the very beginning. All of the energy is accounted for. So doing these energy bar charts is kind of like good accounting problems, keeping track of the energy. All right. Last part here real fast. It says, in a subsequent experiment, a block with mass 2m is subjugated to the same conditions as the original block. The new block is made of the same materials as the first block. That means the coefficient of, the coefficient of friction is the same there. So mass of 2m, coefficient of friction is the same mu. Indicate how the values would change here. So velocity, would our velocity increase, decrease, or remain the same if we had a block of mass 2m? Your tendency is probably to guess that it wouldn't change because it always cancels out in energy, and you're actually right in the end, but let's make sure why here. So our gravitational potential energy that we start with is not only equal to our kinetic energy in the end, but this time we got to subtract out any work that we did. So we really got to make sure that everything still cancels out with this added in here. So gravitational potential energy is mass times gravity times height, and kinetic energy is 1/2 times mass times v squared. So that's what we're used to, canceling those. But let's take this out. This is some force of friction times distance. Well, what's the force of friction? It's mu times normal force, except it's on an inclined plane. So the normal force will be equal to the perpendicular component of gravity, which is mg cosine theta. But here's the key, m's all around. So it does wind up canceling out, but be careful there. It's not as simple as we are used to. Finally, it says, does the distance the spring compresses, does that increase, decrease, or remain the same? Well, if we have a bigger mass to start with, then that means we will have more gravitational potential energy to start with, which means the number of the kinetic energy will be bigger. Even though it's got the same V, it's got more mass. So with that same V, it's got more kinetic energy. And more kinetic energy means we've got more ability to compress the spring, or more spring energy to give, and that means more distance to compress the spring. So it will increase the distance that the spring is compressed.